Hello students, today we will discuss another topic relating to the fourth module here. Okay, uh, the topic that today I am going to discuss is radiation resistance of a short electric tripod. And another topic which is related to this same topic here, that is radiation resistance of a short electric tripod only, but we are specifying the particular length here. Length is equal to lambda by 2 here, right? These two topics I'm going to discuss in this particular session here. Okay, let us consider short electric tripod, as you can see in the figure here. Okay, whose radiation resistance I need to calculate here. Okay, so the length has been given as capital L here. Okay, and through this particular short electric tripod there is a current that has been flowing here. Okay, and plus q and minus q has been represented here. So what is exactly the short dipole? You have to understand here. It is just nothing but a simple wire here of a particular antenna here, whose one end is open circuited and another end is what you can say that it is fed with some power supply, or you can say AC power supply here, right? So usually this particular short dipole is going to have the frequency range of 3 kilohertz to 30 megahertz here, and usually it is helpful in it is used as a receiver here, especially when we are trying to have a low frequency receivers here. Okay, so and usually this particular length of this particular wire is there now, it should be shorter than the wavelength which is going to be operating here. Okay, so this is what is a short dipole here, right? The next point which I'm going to mention is regarding the pointing vector here, right? So what is this pointing vector? Pointing vector is nothing but here which is going to give us the magnitude and the direction of the particular energy here, or a flow of energy here. So we are going to calculate, or I can say the pointing vector of the far field is integrated over a large sphere here, uh, to obtain the total power radiated here. Okay, so if we are going to calculate the total power radiated by this particular short dipole whose length is L here, this power should be equated to I square R here, where it has been given here I square R here, capital I square R here, where I is nothing but here RMS current on the dipole here that has been flowing here. And what about this capital R? Capital R is nothing but here a resistance here, which is also called as a radiation resistance of a dipole, which we are going to find in this particular derivation here, right? Or in this particular topic here. So what about the far field components relating to this particular short electric dipole here? Okay, so we have electric and magnetic field both here. So we have in one particular direction electric field in the direction of theta and magnetic field in the direction of phi here, right? So if at all I wanted to represent in terms of the pointing vector here, both magnitude and the direction, then the radial component is given by SR is equal to, I have written in this equation here, SR is equal to half real part of E theta and H conjugate phi here, right? So both E theta and H phi conjugate uh, are both complex here. So if at all we find the average pointing vector that is given by S is equal to 1 divided by 2 RE, that is real part, E into H conjugate here. So how exactly these far field components are being related here? Okay, so these far field components are being related in the medium through some intrinsic impedance here. That is nothing but here Z, as I represented here in this particular equation here. So E theta is equal to Z into H phi here. Okay, you know the value of Z. Z is equal to again root mu divided by epsilon. You can substitute in this particular equation here. Now, how exactly we are going to find the total power that has been radiated by this particular short electric dipole? As it has been written in this particular equation here, it is being integrated over a large sphere here. Okay, when we consider large sphere here, so double integration of whatever the radial component we are going to get here, that is in terms of SR, that is E theta and H phi here, and into ds here. Okay, that could be written in this particular equation here. It is here you can see here. H phi square R square sin theta d theta here. ds is there, no? This ds could be written as R square into d solid angle here. You know this particular thing which we have discussed in the previous cases here. That is R square into d solid angle. Solid angle could also be written as sin theta, d theta, and d phi here. Okay, that's why we have written here r square sin theta d theta and d phi here. Okay, so this is, you already know here, mu divided by epsilon root is there. No, this is nothing but here your z here, impedance here. So you are substituting the value of e theta here. Okay, e theta here, so that you will get the value of 1 by 2 root of mu divided by epsilon, then h phi square here, right? So that's what you got here in this particular case here, right? So now once you got this particular equation, total power that has been radiated here, now there are certain assumptions that we have to consider regarding the magnetic field here. The magnetic field value which we are having here, h phi as a magnetic field, will be considered as a absolute value of the magnetic field here. Then we'll have standard equation that has been there. Need not worry about this equation. You have to remember this equation here as you have to substitute here. Now what is that equation here? Equation is nothing but here omega I naught L sine theta divided by 4 pi c into r here. This equation you have to substitute in the above equation here, right? So what is this h phi here? H phi magnitude is given. So now what is this w here? W is nothing but here, you can also write in terms of 2 pi 2 pi f or 2 pi by lambda, you can write here. So if at all 2 pi into lambda f you are writing here, so by squaring this one we are going to have 4 pi square f square we are having here. So what is f here? F is equal to c divided by lambda here again, right? So if f is in terms of square here, so c square by lambda square here. So what is going to happen here is that c square in the numerator will get cancelled with the c square in the denominator here. Anyway, r is there here, r square and r square will get cancels here. Okay, sine theta, one term is there here, and here also there is one term sine theta. If you make it as a square here, sine square into sine will come into here, that's why you'll get a sine cube here. So once and anyway that I naught square will come out, L square will come out here, and pi square will come out as usual. R square and c will get cancels here. 4 will be remaining here. If you make a square of this one, it will be 4 into 4, 16, 16 2s are the two term which is constant outside this particular integration will be multiplied here. So hence you will get here 32 here, 1 divided by 32 root of pi divided by epsilon beta square. I will get a beta square here. Okay, 2 pi by lambda is there, no, lambda square we left here. So that again it is not 2 pi here. If you square it, it will be 4 pi square here. So 4 pi square divided by lambda will get you beta square here, right? So overall, if at all we try to substitute this particular h phi magnitude and square here in the above equation, we will get this total field here. Whereas p is equal to 1 divided by 32 root of mu divided by epsilon beta square I naught square L square divided by pi square double integration of sine cube d theta d phi here. Now as a standard form here, the standard form, double integration of sine cube d theta d phi will be having a value of 8 pi divided by 3. This equation can be taken directly here, or this value can be taken directly. So if at all I take 8 pi by 3 as a direct and substitute in the above equation, we'll be having this power equation. P is equal to root of mu divided by epsilon beta square I naught square L square divided by 12 pi here. Now this particular power has to be equated with what here? We have discussed in the first initial stage here. It should be equated to I square R here, right? Where I is a RMS current here, R is nothing but here your radiation resistance of a short dipole here. Now if at all you substitute here, so you know the RMS value here, that is I naught square divided by root 2 here. If at all we try to square it, we will get I naught square and divide by 2 we will get here. So I naught square in the RHS side will be cancelling with the I naught square in the LHS side here. So these two get cancels here. 2 is there here. Okay, right? So 2 at 12 is there here. You will have a 6 pi here. So what is R naught here? Sorry, R naught or RR here. That is RR, radiation resistance here. Radiation resistance is equal to root of mu divided by epsilon beta square L square divided by 6 pi here. Okay, you know the value of beta here. That is beta is equal to 2 pi by lambda here. Beta square we are having 4 pi square divided by lambda square we will be having here. Okay, what about this mu divided by epsilon? If at all we consider for air or vacuum here, it is 120 pi here. Okay, so this term will be 120 pi and beta square will be 4 pi square divided by lambda square. If you substitute those two values in this particular RR, we will be having the final radiation resistance equation as 80 pi square L divided by lambda whole square here. Okay, so this is what is the final answer related to the short dipole of a short electric dipole here. Okay, so whose radiation resistance is given by Rr is equal to 80 pi square L divided by lambda whole square, or you can also write as 790 into L suffix lambda square here. Okay, this is how we can derive or arrive the regarding the radiation resistance of a short dipole here, whose length is L here. Right? We are not specifying any kind of a length at this particular point here. Now there is another topic here which I want to discuss, as I said in the initial here, that is radiation resistance of a that is the same short electric dipole only, but we are explicitly specifying the particular length here. That is, length is equal to lambda by 2 here. So let us discuss this particular topic here. Again, the same equation we have to take here, that is total power P radiated by a short electric dipole is given here. That is P is equal to, again, double integration of SR, that is radial component here, into ds. Again, you have to write the same equation which I have described in the just now 5 minutes before here, that is double integration 0 to 2 pi 0 to pi h5 whole square r square sin theta d theta and d phi here. Right? Again, we have to consider the h phi as absolute value here, but in this case now we have to change it. We have a different equation which you have to substitute here. That is, you can see in the equation number 2 here, h phi is equal to j into I naught divided by 2 pi r cos beta l cos theta by 2 minus cos beta l by 2 divided by sin theta here. Now, if at all we consider only the real part, neglecting the complex conjugates here or complex j here, then we'll having the same equation. Just remove the j component here, equation number 3. Now, if at all we substitute the equation number 3 in equation number 1 here, that is total power P radiated by a short dipole here, then we will keep having this particular equation here. You can see here, what you can do here is, you know the value of root mu divided by epsilon 120 pi here, you can substitute that value here. Okay, suppose if you do that one here, and here we have to have the square value here, I naught square will come into picture here, I naught square will come into picture, and 4 pi square r square will come into picture. Okay, then into 120 pi will be there here, divided by 2 will be there here. So you know here that even the r square will come into picture, r square get cancelled here. Okay, so 120 divided by 2 will be 60 here, and the 60 will be again divided by 4 here, that is 15. So you get 15 I naught square. Okay, 15 I naught square divided by pi here. Okay, and again the double integration of cos beta l into cos theta minus of cos beta l plus sin theta. Now again, if at all we have here theta and phi as an integration here, if you just take out the value of phi here, that is 0 to pi is there here, 0 to sorry, it is 0 to 2 pi here. So if at all we take the 0 to 2 pi here, we don't have any term concerned with the phi here. So 2 into 15 I naught square divided by pi into that pi will come into picture. Pi get cancels here. 15 into 2 we will have 30 I naught square here. Now again the same thing here. What we can do here is, you have to, after getting the total power from the short electric field here, what you have to do, you have to equate it to the I naught I naught I square r here, right? I square r here, that is I is nothing but here RMS value, and r is nothing, r naught here is nothing but here radiation resistance here. So you know the value of I here, that is I naught divided by root 2. If you substitute that one, you will be having this particular equation, that is I naught square r naught divided by 2 here. So P is equal to I naught square r naught divided by 2. Equate this particular to this power equation here. So you'll be having r naught is equal to what? How much here? R naught is equal to 60 0 to pi cos of beta l by 2 into sin cos theta divided minus of cos beta l divided by 2 divided by sin theta here. Now, where r naught is what here? Radiation resistance here. Radiation resistance r naught for the maximum current here. That is equation number 4 here. Now we have to simplify this equation so that we get the answer here. So as usual, you know the value of beta here. What is the value of beta? Beta is nothing but 2 pi by lambda. What is the length we have assumed here? In the previous case, we have not taken the length here. Now we have taken the length, that is L is equal to how much here? Lambda by 2. So substituting the value of beta 2 pi by lambda into lambda by 2, what we will have here? Just having the value of as pi here. So if you substitute in the cost terms regarding the pi here, where you are having cos beta L by 2. Beta L is nothing but here pi. Pi by 2 is how much here in cost terms? That is 0 here. So this term gets 0 here. So now what is remaining here? R naught is equal to cos of, sorry, 60 0 to pi cos square pi by 2 cos theta divided by sin theta here. Now just again I have to simplify here. What is it? Cos theta is equal to how much you can write here? Cos theta is equal to, if you write r here, if you differentiate here, you will get minus sin theta d theta dr here. D theta could be written as minus dr divided by sin theta here. So if at all we put the theta value as 0 here, r is equal to 1 you are going to get here in this cost term. If at all you are going to put the theta is equal to pi, you are going to have a r value as minus 1 here. Now substituting this limits here in this equation, and instead of cos theta you substitute r here, so you'll have 1 2 minus 1 minus cos square pi r divided by 2 divided by sin square theta here. Okay, so this is what we are going to get here. And you know this, if at all you change interchange the limits here, you are going to either sign to you're going to change the sign here, right? So if you are having the negative here, you will have get the positive if at all you change the limits here or interchange the limits here. So you'll have cos squared into pi r divided by 2 divided by 1 minus cos square theta, that is the divided sin square, you know the value, right? Now just for our cos square theta is nothing but here, what here we are having the value as r here, right? So 1 minus r square here. So we know the value of 1 divided by 1 minus r square here, that is 1 divided by 2 into the bracket of 1 minus r plus 1 divided by 1 plus r here. So you can substitute this value in the above equation here. What are we going to get? R naught is equal to 30 into integration of minus 1 to 1 cos square pi r divided by 2 divided by 1 minus r into dr plus minus of 1 to 1 integration cos square pi r divided by 2 divided by 1 plus r here. Now we have to integrate these both the terms here, that is minus 1 to 1 and minus 1 to 1, having the denominator different here, 1 minus r and 1 plus r here. So substituting the value of 1 minus r is v and 1 plus r is equal to u. Just substituting the limits here, we will be getting as r is equal to, if at all r is equal to minus 1 here, you will get v is equal to 2, r is equal to 1, and v is equal to 2 you are going to get here. Okay, r is equal to minus 1 means u is equal to 0, r is equal to 1 means u is equal to 2. We are going to substituting the limits here, so we'll have this value. Okay, so after again just interchanging the limits here, we'll be having 0 to 2 here, sin square pi v divided by 2 divided by v here dv. The same thing will be there, just replacing the v with u here. Okay, now you know this integration here, that is a to b. Okay, limits are there, x dx is equal to, what are going to have, a to b y dx here, both are equal. Then what you can write here is, you can just write 2 into the integration of 0 to 2 sin square pi u or pi b divided by 2 divided by u to du here. Okay, so now if at all we take the sin square here, sin square of theta is nothing but here 1 minus cos theta to theta by 2 divided by 2 here, just substituting this thing here. So what are going to get, 1 minus cos of pi u. Okay, pi u divided by 2 is that 2 you can take outside here, just cancel out each other, and you will have only 30 value here. Again just taking this pi u into t here, so you will have u is equal to 0 means t is equal to 0, u is equal to 2 means t is equal to 2 pi. Substituting the limits and substituting the value of this pi u here, you are going to get a final value as 30 into, what you can say, that limit of 0 to 2 pi 1 minus cos theta divided by t here into d theta. This is nothing but your Euler series here. So if at all it is in Euler series here, we are going to get sin of 2 pi. Sin of 2 pi is nothing but 2.44 here. So 2.44 into 30 will be having as a radiation resistance value as a what here, 73 ohm here. So what is this one now? Now this This one is nothing but the value of the radiation resistance of a short electric dipole whose length is lambda by 2 here, right? So once we are going to consider the length as a lambda by 2, you are going to get the radiation resistance as 73. If at all we don't consider the length as lambda by 2 here, we are going to get the radiation resistance in terms of equation as Rr is equal to 80 pi square L divided by lambda whole square here. Okay, these two are the very important derivations from the point of the examinations here. From the fourth model, remember anyone could be getting the examinations here, which would be carrying around 10 marks each year. Remember radiation resistance of a what here? Short electric dipole. Okay, and what you have to get, you have to get the Poynting vector here of a radial component in the far field. Then you have to get the far field component relation here between E theta and H phi here. Then get the equation of the total power radiated and equate it to what here, I square R here. You will get the radiation resistance of the short dipole in terms of particular cal here, that is length here. If at all we have been given as a length is equal to lambda by 2 here, then you have to take the same total power radiated equation here of the short electric dipole, and you have to arrive with a different H phi here. There H phi is different and here H phi is different, that is magnetic field is different here. Okay, then you have to substitute again or equate it to this I square R here. Okay, to simplification is more in the second derivation here. More simplification is if you do the correctly the simplification here, and you will get the value as R naught is equal to 73 ohm here. Okay, so this is the end of this two topics which I want to discuss now. Okay, radiation resistance of a short dipole and a radiation resistance of a short dipole, short electric dipole whose length is lambda by 2 here. Remember, Rr is equal to 80 pi square L square divided by lambda square, and R naught is equal to 73 ohm, or the length L is equal to lambda by 2 here.